Hi all, welcome back to Cracking the FAANG interviews. Today I'm going to be talking about Leetcode problem number 671, which is finding the second minimum in a binary tree. And this problem has become increasingly popular in recent FAANG interviews and has been asked at Microsoft, Google, and Netflix. And something I want to note here is, and I've put an asterisk next to the binary tree. The reason being, this binary tree is a little special. There is a special condition given in the problem, which can help us think of better solutions. Let's dive deep and understand the problem in more detail before we look at solutions. So this is a snippet of the question from Leetcode. What we've been given is a non-empty special binary tree. By binary tree, the definition is the tree would have, any node in the tree would have at max 2 children. It can have 0, 1, or 2. In case of 0, it would be a leaf node. And the sketch I made is for 2 children. And what makes this tree special is what I want to emphasize on today is the value of the root node is the minimum value in the entire tree. So what we have essentially been given is the minimum value and a tree. I want to say binary tree. And what you've been asked to do is find the second minimum. Let's look at a few examples before we think about how to come up with a solution for this problem. So for the first example, we have this tree, and again, let's check if the special property holds. So in this entire tree, the minimum is 2. The second minimum, as you can see, is 5, and the third minimum is 7. The root has the minimum value. And what you are looking for is essentially the second minimum, which is 5. Let me take another example to make the idea more concrete, and we can start thinking of solutions from there. So this is a special example where we have all the nodes have the same value. So the minimum in the tree is 2. There is no second minimum or third minimum and so on. So you can't find a second minimum in this tree. So you return -1. And this condition has been actually provided in the question. So how would you approach this kind of a problem? So the way I like to think about it is whenever you're given a tree, trees typically belong to this family of graphs. The difference is they are directed, meaning a node would be pointing to its child, whereas graphs can be undirected or directed. And again, trees can be of different type, binary tree, binary search tree, and so on. Graphs is sort of the general family of algorithms. And whenever you're given a tree or a graph question, the first thing I like to think about is it's usually a search problem. They want you to find something. In this case, the search query, if you want to think about it that way, is find me the second minimum in this tree. So what we want to think about is how can we search the tree. And to search the tree, you need to be able to go through the tree. There are two popular ways of going through any graph data structure or tree data structure. One is breadth first, second is depth first. This is called BFS, this is called DFS. So it's breadth first search, depth first search. And I'm going to quickly describe this before I move on to the code. In breadth first search, you go through each level in a tree and you search. So you'd first check 2. Once you're done searching here, you go to the next level and you check these 2 elements. So you're going along the breadth here of the data structure or the graph or the tree given to you. Whereas in depth first, you're going to go you're going to start your search here, look at its child, come back, and then go to the other side and look at this node. So it's along the depth or height, as I'd like to call it. All right, so to solve this problem, you can actually pick either of the these two methods. You can follow a depth first approach or a breadth first approach. I'll solve this problem using depth first. It becomes a little more complicated, so I want you to sort of understand the intricacies, since it's a recursive piece of code. But you could surely solve the problem with a breadth first approach as well. And let's look at the code for this. So here I have this function find second minimum value, and I've been given the pointer to the root node. And again, I'm just going to draw out a tree to work through this. And important note is the root value is the smallest as given in the question in the entire tree. So you know the minimum. So if I give you any array, right? Let's forget the tree for a second and internalize the idea. If I give you any array and I tell you find me the second minimum, and I'm giving you the minimum, how do you do that? So the way one would approach it is the minimum value, and you'd compare it with every other value, and anything that is greater than that value could be a candidate for being second minimum. And you'd have to go through the entire array and eliminate, go through all these candidates and figure out if there's anything else that beats this, right? So there could be first minimum, second minimum, and third minimum. So what you essentially want to do is have these two values, the first minimum, which is given to you, and swap amongst these two or compare these two to find the second minimum and go through the entire array. We are exactly going to do that, but instead of going linearly in an array, now we are using DFS to traverse through the entire tree data structure. Here I have a temp value. I'm just calling it result, which is going to be the second minimum value, and I've implemented DFS here as discussed earlier. And for the first thing we do here is the base case, which is if you're at any of the nodes which doesn't exist, you simply return. And the second case is the root value is the minimum, and you're trying to compare the node value, which is where you're at, the node you're at in your traversal, and you're trying to beat what you thought is the second minimum already. So if I find something which is less than the second minimum candidate, it is actually the second minimum, and you go and update your temp value with node.value. So this node sort of gives you a better candidate, and you do this as you go through the entire tree. And as plain old DFS goes, you go to the left child and the right child once you've evaluated the node. And once I am done with this function, I simply just call traverse with the root node that's given to me. And if I could not find anything, and my temp value is back to what I initialized, and I'm using float infinity just as a reference for a huge value. This is the maximum possible value you can represent. That means I couldn't find anything that could give me a candidate, no candidate, and I return -1. Else I just simply return my best match. All right, this is how I had implemented. So let's look at the time complexity and space complexity for this approach. So this is a binary tree, and in the worst case, you could also have a tree which looks more like an array itself. So you could have this structure which you'd have to traverse linearly. So in that case, you'd go through all the nodes, and even if you have a tree which is sort of kind of balanced, I want to call it, which is a best case of binary trees, you still have to go through all the nodes in the tree So the work you're doing here is going through the entire tree, which is going to be O of n. Whereas the space complexity for depth first search, in best case could be the height of the tree. So if it's the best case, and I'm only mentioning the best case for knowledge and understanding, would be O of log n, given it's a binary search tree. But here we have not been given any guarantees, so the worst case could be what we drew earlier, and the space complexity would be linear as well. Awesome. I hope you enjoyed the video, and thank you for watching Cracking the FAANG interviews. Please like, share, and subscribe to the channel for more exclusive content.